Alright, we are now going to talk about line integrals of scalar functions. So what the heck is a line integral? Well, let's say we've got a curve, r of t, and it is a two-dimensional curve. What would it mean to integrate along that? So let me show you some visuals here. Alright, so let's say we have our 3D surface, and we have a path. C is r of t, which would be x of t and y of t. And so it looks something like this, from A to B. Now we have some function that determines a surface. And so we'd say, well, at each point we would go up, and we would say we'd follow this path so that we're always directly above the path in 2D, but we're also on the 3D surface. So what we defined here is sort of a curtain. And the line integral, so in this case the line integral, where we say z equals f of xy, so z is the height. The line integral of f of xy, and we'll go from a to b of some variable t, this is t, defines the curve, is the area of this curtain. So we define a path based on a single parameter t, we draw that path, and then at every point we use the f function to get the height. This gives us a two-dimensional object in space which we can find the area of. So since we are integrating just one variable, this is a single integral, we get area, not volume. Let's do a graph of this to get an idea. Let's do a calc plot. So let's say we have, this is our function, z equals square root of x squared plus y squared. So we get a cone here. And the path we are given, let me write it out. So you can, it's not in the notes, we can add it in here. Z equals square root x squared plus y squared. And r of t is on the curve x squared minus y equals 1, where x goes from 0 to 1. And we could parameterize that by saying x equals t and solve for y. But for now, let's just look at the picture here. So x squared minus y equals 1. So here's x squared minus y equals 1. I'll turn that on. And I'll say x goes from 0 to 1. So what this tells me is if we look at this, we plot out this here, this little curtain here, like I said. And I had it set so z starts at 0. That's why it's not going below the x-axis. X goes from 0 to 1. Because if x is 0, then y is 1. If x is 1, then y is 0. Let's go to... So what we would be saying is... yeah, okay. There's x equals 0 here, and there's x equals 1 here. So we'd say along this, we'd get this shape, we'd flatten it out, unroll it, and we'd see what the area is. And that's what a line integral means. Since we are measuring some scalar function at every point, and if we think of it as height, then it's the same as area. Now it could be something other than height. Maybe, I don't know, maybe you're collecting electricity as you wander around. You've got some charger that you're using. Who knows? But it's anything that we are adding up as we go along the curve. So, how would we get this integral? Let's define what it is exactly. So as usual, we want to go into Riemann sums to define things. Even if we don't often use Riemann sums to evaluate, they are still the standard way, until you get to analysis 3, they are the standard way of defining how integrals work. So what we would say is, if we were to unroll this curtain, instead of t, we would use the independent variable s, where s would represent the distance traveled, or relative distance. Maybe we can say a is here and b is here. You could shift it sideways. But if we just measure the point every spot along a and b, and this is s, meaning we've straightened out this curve into a straight line, and so we would get something like that, maybe. Excuse me. Now, I'm not saying this is exactly like that curve. It's not perfect, but we would do what we normally do, the Riemann sum. We would divide it up into columns. And in each column, we would say, well, the width is delta S. And we would pick a sample point along there, xi star, yi star. And so then what we would get then is the integral f of xy ds. Well, we would start as usual. We would have the sum from I equals 1 to n. Now we call this delta si, although we usually think of all the delta s as being the same. F of xi star comma yi star delta si. That is when we have exactly n of them, and then we would take the limit as n to infinity. So it's really no different than an integral in Calc 1. It's just that we are traveling along a twisted path instead of a straight line, so we have to be careful to take account of that. So how would we do that? Well, okay, so we have our definitions written in terms of ds. S being the distance we travel along the line. So we need to do some sort of substitution to change ds into dt, because normally we have t as our parameter. S is specifically arc length, and we'd like to be able to not have to use arc length. So we have a formula for arc length. The length of any curve is the integral from the start point to the end point, a to b, of the derivative of x respect to t and the derivative of y respect to t, both squared, added, take the square root, little Pythagorean theorem here, then integrate with dt. So, if this curve, c, integrating f of xy ds, if we plug in t here, we get f of x of t, y of t, times the square root of dx over dt squared plus dy over dt squared dt. If the curve's in 3 dimensions, you just add a third one on for dz dt. So this is the formula, written a little bulky. There's a more compact version on the next slide. When we take derivative of position respect to t, we get our absolute value of r prime of t times square root of dx over dt squared plus dy over dt squared. So what's this saying essentially is that this part here, this dx over dt, dy over dt, has to do with how curved the function is. The more curved it is, the bigger this gets. But this part has to do with how fast we are running along it. So if you want to, ds over dt is velocity. Yeah, but no, velocity, I'm not sure if that's right, because velocity is the shortest distance between 2 points. But it's a vector. But when we write absolute value of r prime of t, we're separating out the speed. Speed is the absolute value of velocity. So we really shouldn't, as usual, we want to factor out those arbitrary ideas like speed. We're looking for the area of a curtain. The area, it should not matter how fast we run along the curve. We should get the same area no matter what. So usually we want to treat the speed as being 1. And then if that's the case, yeah, we will. If it's not 1, then we have to take account of it like this. So let's do some examples, because examples help clarify all this. All right, find the integral along c of 2 plus x squared y ds, where c is the upper half of x squared plus y squared equals 1, traveled counterclockwise. All right, so let's see. Integrate along c of 2 plus, 2 plus x squared y ds. And we said we are going along this curve counterclockwise along the top half of the unit circle. So we want to parameterize this path. So we always, when we're doing line integrals, we would like to change them into an r of t. The circle, did it say unit circle? X squared plus y squared equals 1. Okay, so radius is 1. So that means r of t is cosine t, comma sine t, where t goes from 0 to pi. Now, the formula we had says we also need to have the ds over dt and all that. So we need to get this. So let's do that. Dx over dt is negative sine of t. Dy over dt is cosine of t. So this will become the integral from 0 to pi of 2 plus, now x is cosine, so cosine squared t, y is sine, so sine t, times square root of sine t squared plus cosine t squared dt. Now, what you might notice, and this might help, is that this is in fact just the length of r prime of t. Because r prime of t would be this vector here, negative sine t, comma, cosine t. So the formula we had earlier, if you want to rewrite it, you could just write it as integral from a to b of f of xy with respect to t times the length of r prime of t. So that's the alternate version of the formula. Integral from a to b of f of xy, absolute value of r prime of t dt. Now let me put in x of t and y of t. All right, so let's keep working this out. Well, sine squared plus cosine squared, that's 1. So this becomes 0 to pi of 2 plus cosine squared t sine t dt, which is, let's see, 0 to pi of 2 dt plus, now this part, let's put in a u sub. U equals cosine of t, du equals negative sine t dt. I'll put a minus here, and then a cosine squared t, negative sine t dt. So this will become, okay, this first part is 2 pi minus the integral of, what were we going from 0 to pi? So it's u squared du. Now, if I plug in 0 for t, I get 1. Plug in pi for t, I get negative 1. So 2 pi plus minus 1 to 1 of integral of u squared du, which is then 2 pi plus minus 1 to 1 of u cubed over 3, which equals 2 pi plus 2 over 3. That would be the answer. All right, on to the next. Example 2. Find this integral of x squared minus y plus 3z ds along line segment from 0, 0, 0 to 1, 2, 1. All right, so first thing we need to do is write our parameterization. I'm not going to try to draw a picture because it's 3D and it's not really necessary. R of t is, okay, so let's see. We went from 0, 0, 0 to 1, 2, 1. So velocity vector would be 1, 2, 1 with a starting point r naught of 0, 0, 0. To me, that's the easiest way to do it, but you could also use that 1 minus t formula if you prefer. But then x of t is t, y of t is 2t, z of t is t. So then r prime of t is 1, 2, 1. And then the length of r prime of t is square root of 1 plus 4 plus 1 is square root of 6. All right, so if one integrate c x squared minus y plus 3z ds. It is the same as we just plug in. What are our parameters here? T would go from 0 to 1. So 0 to 1 of t squared minus 2t plus t. And then ds. This here's ds over dt is the same as absolute value of r prime of t. So we replace ds with root 6 dt. The basic idea here is that root 6 is the speed, and so we have to sort of take that into account. Or maybe it's 1 over root 6 is the speed because we're multiplying, and so it cancels it out. That's probably what, well, I'm not entirely sure about that argument, but point is ds over dt is the same as absolute value of r prime of t, so we multiply it through to basically to convert from adding up speed to adding up distance. All right, so root 6, 0 to 1 of t cubed over 3 minus t squared plus, did I leave off a 3 here? Left off a 3 there. All right, that's fine. Could have combined those. 3t squared over 2. So this becomes root 6 of 1/2 minus 2, not the root, 1 plus 3/2. Hang on, let me check my... Ugh. Oh, here's the mistake. It should be a 3. Hopefully, most of you caught that. So it's root 6. Let's see. 1/3 minus 1 plus 3/2. That's 1/3 minus 1/2, or plus 1/2 is 5 over 6. So there it is. 5 root 6 over 6. That's our answer. All right. Let's see what's next. When a curve is piecewise smooth. So what does piecewise smooth mean? Well, it means that it is smooth most of the way, but there are a couple exceptional points. And we've said the definition of smooth is that the parameterization, if you want a single parameterization for the whole thing, it would have to be 0 at these points. So instead of doing that, we're just going to do two separate parameterizations. Do the first one, then do the second one, and add them up. And so this is what's called a closed curve because it comes back to itself. C1 here is the line y equals x. C2 is the parabola y equals x squared. They both go from 0, 0 to 1, 0. All right, so C1 is r of t is y equals x, so it's t comma t. X is t, y is t. T goes from 0 to 1. Now C2 is a little trickier because it's going from right to left. So if that's what we're doing here, from 1, 1 to 0, 0. It's a rule that the parameter t always needs to be increasing. Like I said, I don't have a really convincing explanation for why that's a rule, except that it doesn't seem to work if you break it. So we will say x starts at 1 and ends at 0, so it is 1 minus t. I didn't need parentheses there. Now y equals x squared, so if x is 1 minus t, then y is 1 minus t squared. So now we were evaluating the function was x ds. All right, so the integral along C1 of x ds would equal the integral from 0 to 1 of, so x is equal to t, and then we need the r prime length, which is the length of this would be 1, 1. Or the derivative would be 1, 1. And that works out to square root of 2. So t root 2 dt. Which becomes 0 to 1 of root 2t squared over 2, which is root 2 over 2. So that is the C1. That is this part of the curve. Back path is C2, and that one's going to be a little harder. C2 is, okay, x is 1 minus t. Now, again, we need the r prime, so let's see. I'll mark this in black just so it distinguishes it. R prime of t would be -1, and then 2, 1 minus t times -1. So that becomes -1. And what do we get here? -2 times 2t minus 1. Okay. Or you could multiply this out as t squared minus 2t plus 1. Would it be minus 2? It would be minus 2, wouldn't it? Yeah, that would be minus 2. Thank you. I don't know who I'm saying thank you to. Hypothetical student who was saying, hey, it should be a 2. I assume that was at least some of you. All right, so length of r prime of t would then be square root of 1 plus 2t minus 2 squared. So what we get here is, let's see, 1 minus t times, let's expand that out a bit, make it 1 plus 4t minus 1 squared. If I factor the 2 out of this, it becomes a 4. And then that's the dt, yeah. So r prime of t is the same as ds over dt, so multiply by the r prime and it replaces it. or something like that. Yeah, okay, I said it backwards earlier. Okay, now dt, t will go from 0 to 1. Okay, so this problem's a little ugly. I'm going to erase some stuff, so take a screenshot if you need to. Okay, but I think we want to do a u sub here. And now you could expand this out and collect like terms and whatnot, but to me what I see here is this is basically t squared, and this is basically t. Those are the powers. So it should be that if we make this whole thing under the square root of u, we should make this into a dt. Maybe that won't work. I mean, I have the notes, so I know it will. But you try it out, and if it doesn't work, you try something else. But, okay, I reversed it to be 1 minus t squared. You can write either way you want. T minus 1 squared, 1 minus t squared. Since it's squared, it doesn't matter, because just adding in a negative. All right, so du is then 8 t minus 1 dt. So if I want to make this 8t minus 1, I can still put a negative 8 here and a negative 1 over 8 out here. Then that distributes as 8t minus 8. Okay, so this will become negative 1 over 8 integral of u to the 1/2. Why did I put a negative there? Oh, yeah, because the negative needs to distribute in there. Okay, so du. Now, what are the limits on u? Well, if t were 0, then u would be 1 plus 4 negative 1 squared, which is 5. And if t were 1, then u would be 1. Okay, so that can flip 1/8, 1 to 5 of u to the 1/2 du, which will then be 1/8, 1 to 5 of u to the 3/2 times 2/3, which is, okay, 2/3, so that'd be 1 over 12. 1 over 12, 5 to the 3/2 minus 1 to the 3/2. So our final answer, combining the parts we got from C1 and C2, would be root 2 over 2 plus 1 over 12, and this can become 5 root 5 minus 1. That would be your final answer. All right. Yeah, okay. Now let's look at this next example here. Find the integral along c of x plus 2 ds, where the c is defined by the function r of t is t I plus 4/3 t 3/2 j plus 1/2 t squared k. Okay. So that means r of t is t 4/3 t to the 3/2, 1/2 t squared. So r prime of t is 1. 4/3 times 3/2 would be 2 t to the 1/2. And then derivative here would be t. So then the length of r prime of t is square root of 1 plus 4t plus t squared. So we're going to integrate integral c of x plus 2 ds would equal integral, did we give bound to this? Oh, 0 to 2. Did it say that? I need to add that in. Okay. All right, so x and t are the same thing here. So it becomes t plus 2 square root of t squared plus 4t plus 1 dt. Now this one could be tricky if you didn't notice that this is a perfect square. So keep an eye out for that when you see stuff in a square root. If anything can come out, in this case, the whole thing can come out. It becomes 0 to 2 of t plus 2 square root of t. I lied, didn't I? That's not a perfect square at all. Huh. Well then, I guess we'll go back to the drawing board. Let's try u sub. U equals t squared plus 4t plus 1. du is 2t plus 4 dt. Okay, well luckily then this t plus 2 is exactly half of that 2t plus 4. So we can do our old trick here. We'll put a 2 there and a 1/2 here. And so this becomes 1/2 integral of u to the 1/2 du. And then we plug in the bounds, 0. If t is 0, u is 1. If t is 2, then u is 13. So this becomes 1/2 times 2/3 u to the 3/2 from 1 to 13, which is 1/3 13 root 13 minus 1. That would be your answer. Okay. Let's do a few more. Oh, shoot. Wrong button. All right. Now, sometimes the line integrals are given respect to x and y instead of s. And so we have some notation here. If you see it written as f of xy dx, well, same as before. If we had the integral of f of xy dx, we can put divide by dt and times dt. And then that is a derivative. So what that would mean, if we're doing dx, we're really just multiplying by the derivative and then doing dt. And the same for y. So the formulas are right here, but I think of it as more about a matter of manipulation. You divide by a dt, you multiply by dt, and then the dx over dt or dy over dt become derivatives. So even shorter ways to write it would be p of xy dx and q of xy dy, or just p dx plus q dy. So mathematicians like to use shorthand whenever we can, and so this is how you would shorthand that. So let's evaluate this function. Y squared dx plus x dy along ci, where I is 1 or 2, meaning here's c1, here's c2. I want to do both of them. I want to see if I go along this path, is it the same as if I go along this path? So let's see about this. I'm not 100% sure about the interpretation of this. When it says dx, to me it seems like maybe there's a easterly wind that you're working against, but I'm not sure if that makes sense. Basically, you're not adding up area anymore. You're adding up how much x is changing rather than how much the distance has changed. But again, an actual engineering or whatever interpretation of that is a little beyond me at this moment. Okay, let's get our parameterizations. C1, so R1 of t. This is going from -5, -3 up to 0, 2. So this becomes 0, 2, t plus -5, 3, 1 minus t. We're using the line segment formula. Now we have to combine these if we're going to get a derivative here. It'd be, well, there's a couple ways to do it. Actually, we could do the derivative from here directly. We could say, okay, so R1 prime of t would be derivative here with the t, which is go away. It'd be 0, 2 plus negative 5, 3, negative 1. Be 0, 2 plus 5, negative 3 would be 5, negative 1. That doesn't match my notes exactly. Let me just make sure I haven't made a mistake somewhere. Yeah, you're screaming at the screen right now, telling me you made such an obvious mistake, right? Oh, back here, this was negative 3. That's negative 3. So this should be a positive 3. So it's become 5, 5. So then the length here, R1 prime of t, is length of 5, 5, which would be 5 root 2. And actually, finding the length of r was not even necessary, because what we are doing here is we're saying y squared dx plus x dy along C1. So we actually don't need the whole speed. We just need the two parts. It's dx dt and dy dt both happen to be 5. So this would become, and this parameterization goes from 0 to 1. That's the way the line-segment formula works. So 0 to 1 of, okay, so if y is, okay, we never got y. I guess we need to work that out. I guess when I said we could shortcut this, that was naive of me. All right, so 0 to t plus, let's see, negative 5 times 1 minus t would be negative 5 plus 5t. And then the other part would be negative 3 plus 3t, which comes out to negative 5 plus 5t, and then negative 3 plus 5t. Our t goes from 0 to 1. Okay, so we'll replace the y with negative 3 plus 5t, or 5t minus 3 squared. Then dx is this 5 over here, or the derivative of this, which is 5. 5 dt, plus the integral from 0 to 1 of x, whereas x would be negative 5 plus 5t, so 5t minus 5. No squared on this one. And then dy is also 5 times 5 dt. So that's 0 to 1 of 5t minus 3 squared plus 5 times 5t minus 5 dt. And I'm not going to work all this out. I end up with negative 5 over 6 as the answer. I'm sure you can work that part out on your own. Now, let's do the other one, the C2. All right, so erase all this. All right, so let's do C2 this time. So this is a parabola. Let's look at how it was defined, see if they gave us an equation. They did. X equals 4 minus y squared. probably have worked it. Actually, I don't know if you could work that out. There's probably more than one that goes through those 2 points. Pretty sure there is. So x equals 4 minus y squared. So we're going to set y equals t and x equals 4 minus t squared. We want to do it that way because we don't want to have to solve this for y and get a plus or minus. So then r of t would be 4 minus t squared comma t. R prime of t is negative 2t comma 1. Now we could get the length of r prime, and if this were ds, we'd have to, but it's not ds, it's dx and dy. So this is dx dt, and this is dy dt. So if you multiply by the dt, you get what dx is. So this would be, let's check the parameter of this. Y equals t. Y goes from negative 3 up to 2. So in this case, t would also go from negative 3 to 2. You could certainly rescale this to make it go from 0 to 1 if you wanted to, but there's really no need. The only rule with the parameter is it has to be increasing, and it is. So negative 3 to 2 of, okay, y is t, so t squared, and then dt would be negative 2t, or dx is negative 2t dt, plus, then x would be 4 minus t squared, and then dy dt is 1. So all right, let's clean that up a little. Negative 3 to 2 of negative 2t cubed minus t squared plus 4 dt. And then, once again, I trust you can do this part on your own, so I will skip over it. And I get 40.83 repeating. Okay, so we got very different results from taking those 2 different paths. So that is important to note, then, that we cannot count on 2 different paths giving us the same result. So you have to follow the path that's given unless you're sure it doesn't matter. And we have not yet come up with any way of knowing for sure whether it doesn't matter. So keep that in mind. The path might make a difference or it might not, but you have to be sure if you're going to change paths. Let's do one example in 3D and then we'll call it. C is a spiral, cosine t, sine t, where t goes from 0 to 2 pi. So find the integral with respect along C of y sine of z ds. So in x, y, this just repeats itself, but z is increasing, so this is an upward spiral. So let's just plug in here. R of t is cosine t, sine t, t. T goes from 0 to 2 pi. R prime of t is negative sine t, cosine t, and 1. So the integral along C of y sine of z ds. Okay, so since it's ds, we do need to get the length of r prime. So the length of r prime is square root of sine squared t plus cosine squared t plus 1, which works out to square root of 2. So this becomes integral from 0 to 2 pi of y is sine of t, sine of z, z is t, so we get another sine of t, times root 2 dt. So this one I will do because it's using a formula that not everyone is comfortable with, I think. So we get square root of 2, 0 to 2 pi of sine squared t dt. So we need to reduce the power on this because we don't have a cosine, so we can't do a u sub. So we get root 2 of 0 to 2 pi of 1/2 1 minus cosine of 2t dt, which is root 2 over 2, 0 to 2 pi of t minus 1/2 sine of 2t, which becomes root 2 over 2. We plug in all the stuff. 2 pi minus 1/2 sine of 4 pi minus 0 plus 1/2 sine of 0. Those are all gone, so we're left with a final answer of root 2. Let's see. Yes, that 2 and that 2 divide out, so it'd just be root 2 times pi. All right, that's everything. Thank you for your time.